Chapter 8 is concerned with advanced theories of covalent bonding, and we're going to look at two different theories of bonding: the valence bond theory developed by Linus Pauling and the molecular orbital theory. Molecular orbital theory is the current gold standard as far as theories of covalent bonding are concerned, and it's the one that is currently the dominant theory that chemists use to study bonding. So, valence bond theory recognizes that there are some weaknesses within former bonding models such as Lewis structures and VSEPR theory. So, for example, VSEPR theory allows you to predict the shape of many molecules, but it doesn't allow you to predict things like bond energies or bond lengths. The other difficulty with Lewis structures and VSEPR theory is that they're completely unrelated to the quantum mechanical model of the atom that we developed back in chapters 6 and 7. So the question becomes, is it possible to develop quantum mechanical models of molecules? So Linus Pauling, he was the first to kind of seriously pay attention to this, and his first attempt at doing this led to the development of valence bond theory. So valence bond theory extends the use of quantum mechanics to explain the bonding between atoms, in particular covalent bonding. And in valence bond theory, you have a pretty simple idea, and that is that a covalent bond forms when singly occupied orbitals of two atoms overlap. So that's important. So you have one orbital that's got one electron in it overlapping with another orbital that also has one electron in it, and that's what we call a bond according to valence bond theory. So here's a good example here. We now need to be thinking about atomic orbitals. These are orbitals that are on individual atoms, on two different atoms. In this case, we're looking at two different hydrogen atoms combining to form a bond. So two hydrogen atoms come together, and they each have one electron in a 1s orbital. And so you bring these two hydrogen atoms together, and these singly occupied orbitals overlap, and what we end up with in the hydrogen molecule is two electrons in that overlap region. But you can see in the overlap region, the spins actually obey the Pauli exclusion principle. That is that they flip, so we have one going up and one going down. And it's the overlap region here, this thing here, that's what we're calling the bond. That's how a bond forms. Two orbitals on two different atoms overlapping forms a covalent bond according to the valence bond theory. Important thing here is that one electron from each atom. So the strength of the covalent bond in this model depends on how well those orbitals overlap. And the greater the orbital overlap, the stronger the bond. So the strength of the bond is dependent upon the orientation. You can't have an orbital that's oriented in the x direction overlapping with an orbital that's oriented in the y direction. It's just not going to work. And the other thing is that the orbitals need to be of similar size. If one orbital is very, very small, it's not going to overlap very well. So the orbitals that will overlap are those that can maximize the extent of overlap. So orbitals that are oriented in the x direction will overlap with other orbitals that are oriented in the x direction. Big orbitals overlap with big orbitals, small orbitals overlap with small orbitals, and so forth. So let's look at a molecule where we have two different atoms involved, and we're going to look at hydrogen fluoride. So we've got a hydrogen atom and a fluorine atom, and remember, it's the valence electrons that are going to be forming bonds. So the hydrogen atom only has one electron. It's in a 1s orbital. It has one valence electron in an unpaired orbital by itself. Fluorine has a helium core, and then its valence electrons are 2s2, 2p5. And so we see that the 2s is completely full. That can't form a bond. And then some of the 2p orbitals are completely formed, but here it is. We've got our singly occupied p orbital that's available to form a bond according to valence bond theory. So it's going to be this orbital overlapping with the 1s that's going to form the bond. Okay, so that's what's happening here is the half-filled 1s orbital on the hydrogen atom is overlapping with the half-filled 2p orbital on the fluorine atom, and then there they are, that overlap region there, that's your covalent bond. Pretty cool, huh? So what do we end up with when we overlap these orbitals? Well, in the overlap region, you get an increase in electron density. And when that increase in electron density is along what we call the bond axis, the line joining the two atoms, we describe that as being a sigma bond. So what we're really saying is if we have atom X here and we have atom X here, and they overlap their orbitals in such a way as to increase electron density along the line that's joining the center of those two atoms, we call that a sigma bond. And the important thing to remember is that all single bonds are sigma bonds, and any bond involving s orbitals will be a sigma bond. Now, when p atomic orbitals overlap, they can do it in a couple of ways, but one way that they can do it is side-on. And so we have an atom X here and an atom X here, and here's a p orbital with its two lobes and a p orbital with its two lobes. And if these guys interact side-on, you can see that we don't increase electron density along the line joining the centers of those two atoms. We end up with an increase in electron density above the line joining the two atoms and below the line joining the two atoms. So it looks kind of like what's illustrated in the green there. So when we have this side-on overlap of atomic orbitals, we call that a pi bond. And we get increased electron density above and below the bond axis. Now, something that's important, and we'll come back to this later on, is that a triple bond is always one sigma bond and two pi bonds, and a double bond is always one sigma bond and one pi bond. And if you remember, we said a single bond is always a sigma bond. Okay, we'll revisit that idea later on. Okay, so that concludes this first section of Chapter 7 and Chapter 8. And I'd like you to attempt these homework problems here, and we'll be going through that on the Wednesday question and answer session.